Topic is computational complexity, and before going into the topic, let me just define what is asymptotic analysis. So we have two different branches like time complexity and space complexity. Time complexity is actually the time taken by program to complete its execution in terms of input size, and this time complexity is independent of the programming language used, the number of test cases, and before even writing the program, we could guess the time complexity of the program with the function or the code snippet or the algorithm. Space complexity is actually the space occupied by program in memory in terms of its input size before the execution of program. So how do we say a function f of n would be strictly increasing than g of n is that? For example, we'll take f of n and we'll take a function g of n. We'll say f of n is increasing than g of n if limit n tends to infinity, f of n by g of n is equal to 0, or when limit n tends to infinity, this should be infinity, g of n by f of n is equal to 0. Both the limits should tend to infinity. So for example, let us take two different functions, f of n and g of n. F of n would be n square plus n plus 5 and g of n would be 2n plus 5. Now to find the order of growth, we'll just divide g of n by f of n, and when limit n tends to infinity, 2n plus 5 by n square plus n plus 6. This is the evaluated formula. And well, let us divide this complete equation by the highest growing term, and that is actually n square. So when we divide 2n by n square, it will be getting 2 by n plus 5 by n square, and 1 plus 1 by n plus 6 by n square in the denominator. And when n tends to infinity, what would be getting is that the first term would lead to 0, and here it would be 1, and anything divided by infinity would be 0. So finally the answer is evaluated 0, and we say that f of n is actually strictly growing than g of n. So how do we find the order of growth of a program is like, for example, let us take an example, 2n square plus n plus 6. So we say that the order of program is O of n square. How do we find it is, we ignore all the lower order terms like n, 6 constant, we all ignore all linear and constant terms. When the highest order is quadratic, we also remove its leading constant, like 2n square would be having the constant of 2, and we'll be removing that, and finally what remains is actually the order of growth of program. And this order of growth could be represented using different notations like big O, big omega, and theta notation, or small o notation. So big O is actually the upper bound, or worst case, we would be knowing, right? And big omega is actually lower bound, or best case time complexity, and theta is is actually the time bound, or absolute time complexity, and a small o is actually upper but not time bound, and it is worst but not average case. Theta notation is actually the average case time complexity. So how do we know which terms are lower order? So we have an statement that is arranged from ascending order to descending, and let me give you the statement. So this is a general statement. The order of constant would be O of 1, and that is actually less than log of log n, that is less than log n, and in turn less than n power 1 by 2, and that is less than n power 1 by 2. N power 1 by 3 is less than n power 1 by 2, and less than n, and that is less than n square, n cube, n power 4, 2 power n, and finally n power n. Examples of some common loops, like for example, constant operation will be taken by loops running till n and performing constant operation, like we perform addition or subtraction with the counter variable with a constant, then such a loop would be taking constant unit of time. Also, like for example, here's a function that takes n as a parameter and it finds the sum of n natural numbers using mathematical function n into n plus 1 by 2 using mathematical operators, and this function would indeed take 1 unit of time. So it is actually O of 1. And let me now give some examples for constant operations and log of log n. So here's example of O of 1 operations, O of 1 taking functions. Like for example, we have a counter variable I moving from 1 to n, and we add a positive constant with all the counter variable iterations. So the time complexity, the second one also same, and we start from 0 till n. and we start from n till 0, and we decrement the counter variable with a constant operation, with constant. And time complexity of a function would be considered as O of 1 if it doesn't contain any loop, recursion, and call to any other functions, non-constant time functions. So it would not take, it would always take O of 1 units of time. So here let us take another example for log and unit of time. So whenever we perform multiplication or division of a constant with counter variables, that function would always take log and units of time. Like this I is equal to 1, I till n, and I into is equal to c. Like we multiply every iterated I variable with a constant, and that would result in O of log n. Or if we divide, if we perform division operation also, we would be getting O of log n units of time. So starting from 2, we go till n, and we call the power function. Whenever we call an mathematical function from a counter variable, that would result in O of log of log n units of time. And this is actually O of m plus O of n. It's actually a sum function that takes a variable n as parameter, and it finds the sum of n variables, sum of n natural numbers, and we run a loop from 0 till n, and we increment every counter variable with 1, and finally we add the values of I with the sum, and we return the sum, and finally the time complexity will be O of n.